for.
Okay, hello folks. So I'm the guy from the YouTube videos. Nice to see you all in person, this is cool. So Addie's traveling this week, she's not here. So I'm covering for her, so we're going to do a bit of new content. Okay, so in a calculus course, we always do three things. We do differentiation, optimization, and integration. And today we're going to get into the integration portion of this course. So before we head there, I just want to go back and remember how things are in first year calc, and that will kind of get us ready for how things work in multiple variables. Okay. So in one variable, we have the following picture. All right, we have a function. We calculate the area of that function between a and b by adding up a bunch of lengths. Right, so the notion is that take a bunch of lengths, add them up, you get an area. And the way that we do that with calculus is we say the area is the integral of the function, right? These lengths are the outputs of our function. We add them all up, we get an area. So what we're going to do now is we're going to generalize this to the next step, and we're going to go where we add up a bunch of areas and we get a volume. Okay, so we will sum up or integrate a bunch of areas and we'll get the volume under some surface. Okay. Just to check, folks in the back, is this an okay size? It's readable? Cool. So I want to find the volume under this thing. So we've got a plane, it lives above a rectangle, we want to calculate area. Okay, so in this region, our x is going to run between 0 and 1. And our y is going to run between 0 and 1. Okay, now, over top of that, we're going to have this surface. So we'll look at a couple of these key points. Those are points of intersection, and we'll plug those into our function and get a bunch of heights. Okay, so we plug in 1, that gives us 1, 0, 1. 1. So now we're going to connect up those 3 dots with a plane. Okay, so our plane runs something like this. So you can sort of imagine like you have a cylinder, or sorry, you have like a vertical pillar. Right? So you have this pillar going up, and then you cut it with a plane. Okay, so our approach to finding volumes is to integrate out areas. So for this example, we're going to draw in some of these areas as slices, and then we'll get into setting up this thing as an integral. Okay, so if I set x to be 0, then I get this slice. So this is the x equals 0 slice. Copy that guy. Get something like that. Is it clear where that thing lives? Just want to check. Right, we shave off when x is 0. We're just taking one side of this thing. Okay, now we're going to come all the way over to the other side of it. We're going to take the x equals 1 slice. Okay, so that's on the opposite side of this post. So as we slice this object, some of the slices come out as triangles, then other ones come out as these weird 4-sided things. The shape changes as we move through the object. Okay, so what we want is a formula that will calculate out the area of each of these slices. So to calculate that area, we're going to use this first-year calc notion where we integrate out a function. So we want the area at each particular slice. Each of these guys runs from y equals 0 over to y equals 1. Right, so what we're doing is we're increasing our values of y from y equals 0 up to y equals 1. And now we're doing an integral in there. Same thing, y goes to 0, y goes to 1. The thing that's determining the height of these slices is our original function. right? So if we set our x to 0, we should get the area of this slice. And if we say x is 0, we get that it should match here, right? This thing's a triangle of area half, and seems like it matches, so this area function seems nice. Okay, now we want to calculate the total volume under this thing. So what we'll do is we'll add up the area of all these slices. Right, just like we do in first year calc. Get something like this. So this is what we call double integral. We've got an integral in dy and an integral in dx. And now we can integrate it just like we would in first year calc, using exactly the same techniques. So we're going to deal with the stuff inside, the dy stuff first. Plug in our bounds using fundamental theorem of calculus. And now we've got another single variable integral. So the volume of this thing ought to be 1. Okay. Cool. Okay, so thoughts about this procedure? Comments? Yeah, sure.
How did we come up with the x plus y integral?
Right, sure. So the height of these things is this guy, right? So the top of this thing is z is equal to x plus y. The top of this thing is also x plus y, right? So we're always integrating that same height.
Yeah.
Cool. Okay, so this is sort of the story of how we go from areas to volumes, right? We integrate out the areas to get a volume. So one thing I want to point out is that we sort of made a choice of which direction to slice. Here we chose to slice in the x directions. right? So we said, okay, let's change x and take the slices in this order. And we wound up with an integral that looked like dy dx. Right, so we were slicing in the x direction, we got something that looks like this. We could just as well have chosen to go and do slices in the y direction. And then we'd get a corresponding integral where we have these different slices. And what should happen with the two volumes? We calculate it in this order, what should we get? Yeah, we should get the same thing, right? We've got this region. It is a particular volume, and that volume should not care whether we're slicing like this or like this. The volume should stay the same. So let's try it. Okay, so in the back of our mind, we hope that this equals out to the calculation we got before.